Hi folks, this video is going to be on hydrogen bonds, and we're going to refer back to covalent bonds that we covered in lecture. And I want you to remember what our water molecule looked like. So remember that oxygen had 6 valence electrons, and so it needed 2 more to complete its outer shell. So it shared 1 electron with each of 2 hydrogen atoms. So we can see that sharing right here. And altogether, that made a water molecule. Now, when we draw this molecule on a flat piece of paper like this, we can't really see its 3-dimensional structure. The 3-dimensional structure is all around the nucleus. In other words, these electrons don't just occur in a flat plane. They actually are all over the place around that nucleus. But if they're all electrons, if we think about this pair of electrons and this pair of electrons and this pair, remember electrons are all negative. And negatives repel each other. So they want to get as far away from each other as they possibly can. To do that, they have to form a shape called a tetrahedron. So if we think about this black ball as being the nucleus, and we think about these white balls as being pairs of electrons, the way they get as far apart as they possibly can from each other and maintain their distance from the nucleus so that they're really orbiting all around the nucleus. The way they get that far apart is by forming this shape called a tetrahedron. It's actually like a pyramid on every side. So it's like triangular. There's a triangular area here, there's a triangular area between these 3, and a triangular area between these 3. So it's very, it's kind of like a pyramid, but not exactly, because a pyramid is really 4 sides, so it's square on the bottom. This is like a pyramid that's a triangle on the bottom. It's called a tetrahedron. In some molecules, this tetrahedron, like when you learned about methane in lecture, it's very equal because these would all be 4 hydrogen atoms surrounding a carbon atom. Water isn't that much different than methane. So theoretically, this picture would be a better picture for methane, which is CH4, carbon in the middle, hydrogen, 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 and hydrogen. We're going to use the same structure. It's the same shape. The water molecule is very much the same shape. So look here. Here's a pair of electrons. Here's a pair, here's a pair, and here's a pair. Imagine those forming a tetrahedron. So in reality, these 2 hydrogen atoms that look like Mickey Mouse ears are off to one side, and these 2 pairs of electrons are kind of off to the other side. Let's take a look at that tetrahedron again. Imagine the hydrogen atoms here and here, and the electrons here and here. It doesn't really matter where you put them because all 4 of these spots are identical. So any 2 of these could be the hydrogen and any 2 could be the electrons. It really doesn't matter. The important thing is the molecule is bent. When we think about water, we would have a hydrogen here, and an oxygen here, and these would be just pairs of electrons. So water has this bent look. It's really kind of a 3-sided bent look. And it's bent because these electrons force these pairs of electrons associated with those hydrogens off to the side. Well, if we think about this, that means that there's more electrons on this side of the molecule than well, I won't even say more electrons, but more negative charge on this side of the molecule than this side. We have the same number of electrons, but over here you have protons. And remember, there's a proton here, proton here. Those are positive. In addition, oxygen has, because it has 8 electrons, it also had those 8 protons. It has a lot of protons here compared to the number of protons in hydrogen. So these electrons, hydrogen's electrons, actually spend more time around the oxygen than they do around the hydrogen because they're attracted to that positive charge. So overall, this side of the molecule tends to be where the electrons are hanging out. This side of the molecule has these 2 protons that this side doesn't have. So if we look at the entire molecule, we have equal number of protons and electrons. But if we look at where they are in space, we find that the molecule is polar. There's a distribution of charge so that there's a more negative charge on this side of the molecule than there is on that side. Whenever this happens, we call this a polar covalent bond. It often happens when you have oxygen and hydrogen bonded to each other, which they do a lot. We're going to run into this quite a bit in the near future. So when you see oxygen, or you see oxygen and hydrogen, you're going to assume this oxygen area is going to take on a slightly negative charge because the electrons spend more time here. So that's a single water molecule. Now imagine we put two water molecules together, or we put a whole tub of water molecules together. What's going to happen? Well, each water molecule is going to align with the other molecule. So we're going to have the positive side of one molecule is going to align with the negative side of other water molecules. That attraction between the positive side of one polar covalent molecule and the negative side of another is called a hydrogen bond. So right there, that's a hydrogen bond. These are the weakest bonds of all. And you actually know that because you can stick your hand into water and separate water molecules and pull your hand back out and the water molecules come back together. You can do that, but you know, like those water striders, the spidery-like things that can crawl around on the water, they aren't strong enough to break this bond, to break that bond there. So some things can break the bond very easily, like us, but other things can't. So these hydrogen bonds that hold the water molecules together are responsible for the surface tension of water. Water actually sticks to itself. It also will stick to other things. So it's not, you know, when something gets wet, water is literally sticking to it because there's a charge on that thing, whatever it is. So water will stick to it and make it wet. If there's no charge for water to stick to, so if there's no negative charge for the positive side of water to stick to something and no positive charge for the negative side of water to stick, the water won't stick at all. And that's what happens with waxes and oils and fats. They don't have a charge, and so water doesn't stick to them. And you know, that kind of gives us all the properties. If water actually makes something wet, we know that that thing has a charge. Okay, so in conclusion, hydrogen bonds are bonds between polar covalent molecules, not atoms. Be really clear about that. This is a bond between molecules, and specifically between molecules that are polar, that have a distribution of charge. They're not equally charged all the way around. There's a positive side and a negative side. And when two of those molecules come together, the positive side of one is going to line up with the negative side of the other, and they're going to be attracted to each other. They're relatively weak bonds. Think of water. Water is held together by hydrogen bonds, and you know you can break those bonds. That'll help you remember it.